The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or a name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All right, so today, it looks like we're going to cover a lot, but in 11.6, there's only one small topic we're going to look at. Then we'll go on and take a look at 11.7. And so tonight's assignment, you'll have a short piece from 11.6 and then 11.7 in the chapter review. Tomorrow, Thursday, we'll review during class. Friday, you'll take your chapter 11 test. And then next week, I believe your final, let me check here. I think it's on Wednesday of next week. Yeah. And so Monday and Tuesday of next week during class time, I'll review, I'll come in. Anybody has any questions, we'll go over them. All right. Having said all of that, we are now going to look at some questions that were requested. This is from section 11.5 and starting with problem number 5. Okay. This is another case of fill in the blank where if you're doing it the way I had us do it in class, where you just kind of punch it all into your calculator, you don't necessarily do the individual pieces. But let's take a look at what we've got here. So we've got this formula, A equals P times E to the RT power. You're told that P is 1,000, R is 8% or 0.08, and T is 10. So filling in the numbers, you'd have A equals 1,000 times E to the, let's see here, 0.08 times 10 power. Then, and if we did this a piece at a time, instead of punching that whole thing into the calculator, next you'd get, let's see, you'd take a point or 0.08 times 10, which would be 0.08. And then if you did e to the 0.08 power, so you've got e to the 0.08 power, and you get 2.225540928. And then finally, multiplying that by 1,000, you get 222.55400928. Okay. Now, this is if you did it a little piece at a time. If you took this and multiplied it together first to get that, and then you took that and calculated to get that, and then if you multiplied it by 1,000 to get that. The way we've been doing it in class is to just do all of this at once. So I understand the confusion. It's like, what are they doing here? They're just trying to break it down into steps. Though, again, if you put it all into your calculator at once, it would be fine. So here, what would go, the first thing would be 1,000, okay? And then you'd have the exponent would be 0.08 times 10. So you've got, so your first box is the 1,000 and the 10, okay? Then in the next box, they just multiplied the 0.08 times 10 to get 0.8, okay? And then in the next box, they calculated all of that, so you'd still have that 1,000 out front, and then finally, you'd multiply it all together. Does that make sense?
Yes, I was just confused.
Yeah, I know. It's yeah, because again, if you're punching it all into your calculator, I don't know why I leave that problem in there, but I seem to just keep leaving it there quarter after quarter. Okay, let's take a look at problem number 30 now. Okay. Solve the equation, express your answer to 4 decimal places. So we've got 1.009 equals the natural log of x. All right, so keep in mind that the natural log of x would be the same thing as log base e of x, right? ln natural log base e. This is an exponential equation, excuse me, this is a logarithmic equation. I'm going to rewrite it as an exponential equation, which would be e to the 1.009 equals x. So far, so good? So e to the 1.009 power, and I get 2.742856786. 4 decimal places right there. The 5 would round up 2.7429. So there's the answer to problem number 30. All righty, good to go on?
Yes, on my end.
Okay. Number 37, the quantity of a prescription drug in the bloodstream of a patient T hours after it is administered can be modeled by an exponential function. See the graph. From the graph, determine the time it takes to eliminate half of the initial dose from the body. Okay, so they take the initial dose, 100% of it's in the body. Okay, time goes by in hours. Where is it? Does it have just half the initial dose? Right there. Okay, and so approximately how many hours is that? Well, oops, if we go down, it looks like it's about 8. And our choices make it easy. You know, I might have guessed 9 or 10, but given the choices, it's got to be 8 hours. Okay with that?
Yes.
You don't sound very convinced.
I was thinking 10 too, because I look at it and I even wrote out
Yeah,
there.
you kind of eyeball it. It looks like about 10, but which one of these is closest to 10?
Oh, true.
Yeah,
8.
so you don't have any choice. I mean, yeah, or the choices are slim. All right. 41. How long will it take $8,000 to double if it is invested at an annual rate of 7% compounded continuously? Round your answer to 1 decimal place. Okay, so the principal is $8,000. Okay, the interest rate, annual rate is 7%. Compounded continuously, and we want it to double. So there's 2 different ways we could do this. That's the long way. And then go on from there. But the short way is going straight there. Remember, we looked at that yesterday. So how long would it take? The natural log of 2 divided by 0.07. So, oops, natural log of 2, close it up, divided by 0.07, and I get 9.902, and it said 1 decimal place, so 9.9 years. Okay? Do you want me to go through all of this, or are you okay with this?
I'm okay.
Excellent. I didn't want to do it either because I'm lazy. All right. Here we go. There's that very formula, only now to triple it, it's the natural log of 3. So let's see here. A population growing continuously at a rate r will triple in a time given by the formula t equals the natural log of 3 over r. How long will it take a population of a town to triple if its growing rate is 9% per year? So it's going to be the natural log of 3 over 0.09 because the growth rate is 9%. So natural log of 3, close it up, divided by 0.09, and we get 12.20, so approximately 12.2 years. Okay? Good to go with that?
Yes.
All right, and finally, 43. To estimate the number of hours that a murder victim has been dead, oh, great. A coroner used the formula T equals 1 over 0.25 times the natural log of 98.6 minus T sub S over 82 minus T sub S, where T sub S is the temperature of the surroundings where the body was found. If the crime took place in an apartment where the thermostat was set at 70 degrees, so that means T sub S is 70 degrees, approximately how long ago did the murder occur? Round your answer to 1 decimal place. So T equals 1 over 0.25 times the natural log of 98.6 minus 70 over 82 minus 70. Okay, T equals, well, first of all, what is 1 divided by 0.25? That's 4. And then we're going to have the natural log of, let's see, we've got 98.6 minus 70, which would be 28.6. 82 minus 70, which would be 12. Okay. So we've got 4 times the natural log of the quantity 28.6 divided by 12. Close it up. And I'm getting 3.474, a bunch of zeros, etc. Rounding to 1 decimal place, you'd have 3.5 hours ago. Okay.
That one was a little confusing. I ended up watching the video, but it explained it pretty well. So.
Okay. All right. So now, give me just a minute here. I'm going to switch to some different problems from somebody. Okay. Let's see here. This is still 11.5. Five and 32. Okay. So now all right, we're going to look at another example of number 5. It's basically going to be the same thing. Do you need me to walk through it, or are you okay with it?
I'm okay with it. I understood the first one.
Okay.
I was like, oh, okay.
Then we'll just go ahead and go to 32 then. Okay. Assume that there are no deposits or withdrawals after the initial one. An initial deposit of $4,000 grows at an annual rate of 5.5% for 4 years. Compare the final balances resulting from annual compounding and continuous compounding. All right, so what do we know? We know that the principal is $4,000. The annual interest rate is 5.5%, which is 0.055, and the time is 7 years. Okay. Now, compare the final balances resulting from annual compounding and continuous compounding. So for annual compounding, K is 1, and we're going to be using this formula. Okay, because it's not continuous. So we're going to plug all that information in. A equals $4,000 times 1 plus 0.055 all over 1 to the 1 times 7 power. Okay. So putting this in my calculator, 4,000 parentheses 1 plus 0.055 divided by 1, which again is just basically the same thing. Close it up. Little caret to the power of 1 times 7. I get 5818.716645. All right, to the nearest cent, it would be $5,818.72. And again, I could have simplified that and made that into 7 and made this into 1.055, if I wanted to. All right, are we okay with the first part? Now, the second part, it says continuous compounding. So we're going to use this formula. So we're going to get that. So I've got 4,000 times e to the 0.055 times 7. And I get 5,878.457. That's going to round up. So 5,878.46. Okay, compare the balances. All right, so annual compounding, 5818.72, continuous 5878.46. So you make almost $60 more from continuous compounding.
Okay.
All right with that?
Yes.
Okay, with that, we're going to go on to the new sections. So give me just a minute here. Let's see, actually, I need to do this. So this is going to go away. Now. All right, you see my whiteboard?
Yes.
Let's go back to a problem that I introduced at the beginning of this chapter. And it was something like this. I said 2 cubed is 8, 2 to the 4th power is 16, 2 to the x is, I don't know if I said 10 or 11 or 12, but it doesn't really matter. Let's just go with 10. Okay. I said, well, how would we figure out what x was? Well, for starters, x has to be somewhere between 3 and 4, right? Need to oil this chair.
Yes.
I'm going to take this and write it as a logarithmic equation. So it would be log base 2 of 10 equals x. And I said, the good thing about this is that now we've isolated x, which is what we're looking for. But at the time, and in fact, we still don't know what to do with this because our calculators have log base 10 and they have log base e, but they don't have log base 2. Now, it's possible that one of you does have a calculator that has a button that looks like this. If you have this calculator, you don't have that button, and you're going to need what I'm going to show you. So I'm going to make the assumption that you don't have that button, okay? So what we're going to look at now is something called the change of base formula, okay? What we're going to do, we're going to take log base 2 of 10, and we're going to rewrite it as an expression that uses either log base 10 or log base e, because those we can punch into our calculator. All right. Before we do that, I want to just give you the formula. It says this: log base b of x equals log base a of x over log base a of b, where a and b have to be positive numbers, because remember, the base can't be negative or 0, and you can't take the log of something that's negative or 0. So what does this mean? It means that if we've got log base 2 of 10, we could write that as log base a of 10 over log base a of 2. But I can use any base that's positive or that's not 1, right? So I would either use base 10 or base e. So basically what I'm going to do is this. I'm going to write it as log base 10 of 10 over log base 10 of 2, or natural log of 10 over natural log of 2. And I'm going to get the same answer either way. So I can either use base 10 for A or base E. If I use the top one, so log of 10 divided by log of 2, I get 3.321928, et cetera, et cetera, et cetera. If I go natural log of 10, close it up, divided by natural log of 2, I get 3.321928, et cetera, et cetera, et cetera. I get the same answer, okay? Now, you don't want to mix them. You don't want to have like log base 10 on top and log base E on the bottom. They've got to both be log base 10 or both be log base E or natural log, okay? But this allows us to take an expression like this and split it up and punch it into our calculator, all right? Any questions so far?
Nope.
All right, so let's take a look at some examples to apply this rule. It says, use the change of base formula to find each logarithm to 10 places. Log base 3 of 7. So if I'm going to use log base 10, I'd write it like that. If I'm going to use natural log, I'd write it like that. And I can do it either way, okay? Now, again, recall there's an implied 10 written here, but I don't need to write them there because the notation says we don't have to put the 10 there. All right. So let's see here. Log base 10 of 7. And so you've got log base 10 of 7, and you've got to close that up before you put divided by. Log base 10 of 3, close that up. I'm getting 1.77124, which is 1.7712, rounding to 4 decimal places, okay? And then if I use natural log of 7 divided by, natural log of 3, I get the same thing. And you don't have to do it both ways. I'm just saying you can do it either way, okay? You can use log base 10 or log base E. All right, let's have you do one. Do this, log base 5 of 10. You should be getting 1.4307 when you're all done.
Yes.
So your first step is going to look like this, and then to the answer, or like that, and then same thing. Antonia, did you get that okay?
Yep.
And Karina, you said you did? All right. So that's all we're going to do out of 11.6, and you'll have a few questions in WebAssign just to reinforce how to use that formula, okay? Now we're going on to section 11.7. Give me just a second to regroup here. And I think we are good to go. Okay. The directions say solve each equation. 6 to the x minus 2 power equals 36. Now, in a previous section, we looked at how if we have an exponential equation and we have a base raised to a power equals the same base raised to some unknown power, because exponential equations or exponential functions are one-to-one, we can, if the bases are the same, therefore the exponents must be the same. And if the exponents are the same, therefore the bases must be the same. So I could take this equation and I could rewrite 36 as 6 squared. So now I have 6 to the x minus 2 power equals 6 to the 2 power, which means the exponents are equal. So x minus 2 equals 2, add 2 to both sides, x equals 4. So basically 6 to the 4 minus 2 power equals 36, because 6 squared equals 36, because 36 equals 36. So it checks. Okay with that? It's finally warming up down here. Okay. Any questions on that one?
Nope.
All right. Let's see here. How about this one? 8 to the negative 2x plus 1 power equals 1 over 64. I could take 1 over 64 and write it as 1 over 8 squared and write it as 8 to the negative 2 power. So the goal is to have the same base on both sides. So 8 to the negative 2x plus 1 equals 8 to the negative 2 power. Therefore, negative 2x plus 1 equals negative 2. Solve for x. Again, you see what I'm doing there? I'm getting it so we have the same base. All right, subtract 1, negative 2x equals negative 3, divide by negative 2, x equals positive 3/2. 8 to the negative 2 times 3/2 plus 1 equals 1 over 64. 8 to the negative 3 plus 1 equals 1 over 64. 8 to the negative 2 equals 1 over 64. 1 over 8 squared equals 1 over 64. 1 over 64 equals 1 over 64. Cha-ching, cha-ching. Just checking. Righty? Good to go on?
Yes.
Antonia, we good?
Yes.
Okay. What about this though? Says solve each equation, give the exact solution and an approximation to 4 decimal places. I don't know about you, but I can't think of how to take 12 and write it as 7 to some power. So that process that I was using on the first 2 examples, it's great if I can see how to make the same bases. But if I can't, then I got a problem. Well, I got a problem. This is an exponential equation. Let's change it into a logarithmic equation. Log base 7 of 12 equals x. Well, couldn't I use the change of base formula and rewrite that as the log of 12 divided by the log of 7 and punch that into my calculator? There you go. So log of 12 divided by log of 7, 1.276989408, and it said 4 places. The 8 would round up, so 1.2770. So basically 7 raised to this power would be 12, approximately that power. Since I've rounded that off, if I go back and I go 7 and then the little caret key to what power, and I put in 1.2770, it comes out 12.0002473. So because I rounded, it's not exact, but it's darn close. So this is the approximate solution. We okay with that?
Yes.
All right. How about this one? 5 to the x plus 1 power equals 3. Again, I don't know how to take 3 and write it as 5 to some power. So I'm going to rewrite this as log base 5 of 3 equals x plus 1. To solve for x, I'm going to have to subtract 1 from both sides. So I've got x equals log base 5 of 3 minus 1. And that minus 1 is a whole separate term. Using the change of base, let's use natural log this time. So I get that. So natural log of 3, close it up, divided by natural log of 5, close it up, and then minus 1, negative 0.317393. The 9 would round up, so we get negative 0.3174. I do believe. We okay with this?
Yes.
All righty. Now let's do some using base E. E to the 3.3 t power equals 9.1. So I'm trying to solve for t, which is the exponent. This is an exponential equation. Let's rewrite it as a logarithmic equation. It would be log base E of 9.1 is 3.3t. But log base E is natural log, so it'd be natural log of 9.1 equals 3.3t. But we're trying to solve for t, so we'll divide both sides by 3.3, and t equals the natural log of 9.1 divided by 3.3. So natural log of 9.1, close it up, divided by 3.3, and I get 0.66917, and it goes on from there with the 7 would round up, 6692. All right with that?
Yes.
Okay. How about this one? Log base 4 of 2x minus 1 equals 3. Well, this is a logarithmic equation. So let's try changing it to an exponential equation and see if we can solve it. We get 4 cubed equals 2x minus 1. 64 equals 2x minus 1. Add 1 to both sides. 65 equals 2x. Divide by 2, x equals 65 over 2, or what, 32.5? Whichever way you want to do that. Okay with that? I think I said this a while ago, but I'll say it again. Quite often when you have a logarithmic equation that you need to solve, you solve it by changing it to an exponential equation. And when you have an exponential equation you're trying to solve, you change it to a logarithmic equation. So being able to change back and forth between the two forms is probably the most critical thing in this whole chapter. Okay. Let's see here. How about this one? Log of 3 minus 2x equals log of x plus 24. Just like if you have an exponential equation, when you have the same base on both sides of the equation, the exponents are equal. If you have a logarithmic equation and you have the log with the same base on both sides of the equation, then the quantity you're taking the log of on each side is equal. So from this step, we can go to here. I'm going to solve for x. I'm going to subtract x from both sides. Subtract 3 from both sides. Divide by negative 3, x equals negative 7. Okay. All right, now we have a new formula, and let me explain what it looks like and what it is. This says A equals A sub 0 times 2 raised to the exponent negative T over H. Okay. H stands for half-life. And let's talk about how half-life works. Okay. Let's say that there are 32 Snickers bars in the refrigerator. And I come back 1 week later and there are 16 of them. We'll call SB for Snickers bars. And I come back 1 week later and there are 8 of them. And I come back 1 week later and there are 4 of them. So as each week goes by, half of them will say die off, disappear. So we would say the half-life of Snickers bars is 1 week. Now, 2 half-lives does not a whole life make. In other words, 16 of them disappear the first week, but 16 of them don't disappear the second week. Each time, whatever's there at the beginning of the week, half of that disappears. Okay. And that's the way that radioactive decay works, where you've got a radioactive substance and it has a half-life. Over each half-life, half of what's there at the beginning of the half-life disappears or dies off. So if each time we're getting half of what we had before, it seems like we'd have a base of a half. Remember when we graphed this thing? The value is cut in half each time. So why does this thing have a 2 instead of a half? Well, they could have written it like this. 1/2 to the T over H power. But by making it a negative exponent, that's the same thing as having 1/2 to the positive power. And this particular book did it this way, so that's what we'll go with. All right. So what you've got is you've got your beginning amount. You've got the time that goes by. You've got H, which is the given half-life it takes for half the substance to disappear, and your ending amount. All right. So let's take this formula and let's apply it to some problems. All right. I'm not sure how to pronounce all these chemical formulas or whatever, but I think it's tritium. It says tritium decay. The half-life of tritium is 12.4 years. So every 12.4 years, half of what's there at the beginning of that time disappears. How long will it take? So time is the unknown, for 25% of a sample of tritium to decompose. 25% decomposes. Now, they did not tell us how much we started with. They did not tell us how much we ended with. What they did tell us was that 25% of what was there disappeared, it decomposed. So if our beginning amount is A sub 0, our ending amount would be 75% of A sub 0, or 0.75 times A sub 0. Okay. Remember the problem we did yesterday with the doubling? We didn't even know what the principal was, but we had P on one side and 2P on the other because it doubled. This is the same kind of thing. We don't know what the starting amount is, but we know that we lose 25% of it. So at the end, we have 75% of it. So this is going to go in there. So we're going to have 0.75 A sub 0 equals A sub 0 times 2 raised to the negative T divided by 12.4 power. Okay. So the exponent is negative t divided by the half-life. Any questions so far? All right, in my next step, for my next trick, I will divide both sides by the beginning amount. So I get 0.75 equals 2 to the negative t over 12.4 power. This is an exponential equation, and my unknown is part of the exponent. So I'm going to change this into a logarithmic equation, and I'll get log base 2 of 0.75 equals negative t over 12.4. To solve for t, I'm going to multiply both sides by 12.4, but I'll multiply by negative 12.4 so that I not only get rid of the 12.4 in the denominator, but I get rid of the negative in front of the t. So now I've got negative 12.4 log base 2 of 0.75 equals t. So t equals negative 12.4. I'm going to use the change of base, log of 0.75 divided by log of 2. That goes into the calculator. Negative 12.4 log of 0.75, close up with parentheses, divided by log of 2, close up with parentheses. And I get 5.1464. Let's see here. And they're going to round to the nearest tenth of a year. So it's going to be about 5.1 years. Now, a lot of algebra went on there. Did I lose you anywhere?
Okay, I kind of got lost when you changed it to negative 12.4.
Oh, okay. So I had negative t over 12.4. So by multiplying it by negative 12.4, the negatives became positive.
Oh, okay.
Otherwise, I would have had negative t, but I didn't want negative t. I wanted positive t. So
Okay.
I just took care of it all at once. All right. We good to go on?
Yes.
Next question says radioactive decay. In 2 years, 20% of a radioactive element decays. Find its half-life. So we're going to use this formula. Okay. We know the time is 2 years. We know that 20% decays. We don't know the starting amount. We don't know the ending amount, but we know that 20% decays, so the ending amount would be 80% of the starting amount, which I could just write as what? 0.8 a sub 0. I don't need that 0.80 afterwards, okay? And we're trying to find the half-life. So I know the time, I know that 20% goes away, so the ending amount is 80% of the beginning amount. A is 0.8 times a sub 0. We ready to go on with the problem?
Yes.
All right. So 0.8 a sub 0 equals a sub 0 times 2 to the negative 2 divided by h power. All right. My next move is going to be to divide both sides by a sub 0. So I get 0.8 equals 2 to the negative 2 over h power. I'm trying to solve for h, which is part of the exponent. So I'm going to take my exponential equation and rewrite it as a logarithmic equation. Log base 2 of 0.8 equals -2 over h. So far, so good?
Yes.
Now, let's go back to the previous problem. Back here, t was in the numerator, so I needed to get rid of the negative and the denominator. But here, h is in the denominator. So I can't multiply both sides by -2 and have it go away. What I need to do is this. I'm going to multiply both sides by h. That gives me h log base 2 of 0.8 equals -2. I haven't solved for h, but at least I have h on top now. So my next move is going to be to divide both sides by log base 2 of 0.8. Okay. So now I have h equals -2 divided by the log base 2 of 0.8. I've isolated h, but I'm not quite ready to put it into the calculator. I need to use the change of base formula. Let's use natural log. So natural log of 0.8 divided by natural log. Let's clean that up a little bit better. Natural log of 0.8 divided by natural log of 2. Now, I'm also going to need to group this whole thing. So on my calculator, I'm going to go -2 divided by parentheses, and then the natural log of 0.8, close up that set of parentheses, divided by the natural log of 2, close up that parentheses, and then have another right parentheses that represents the blue here. And I get 6.21256. Let's see, what does it say? They do it to the nearest 10th of a year, so approximately 6.2 years. You okay with this?
Yes.
All right. Let's see here. One more of these. Carbon-14 dating. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that it's assumed to have had initially. How old is it? All right, now, it tells you in the reading that the half-life for this is 5,700 years. That's not something I would expect you to know. If they give you a problem like that, it'll tell you in the problem, okay? How old is it? So we want to know how much time has gone past. That's the unknown. Again, I don't know the beginning amount, and I don't know the ending amount. Now, here's the deal. The first two problems I had, the first one said, how long will it take for 25% to decompose? So we ended with 75% of what we started with. Okay. The second one said 20% of the element decays. So we ended with 80% of what we started with. This one says a bone fragment analyzed by archaeologists contains 60%. So it's not telling you what it lost, it's telling you what it still has. See the subtle difference there?
Yes.
Okay. So 0.6 a sub 0 equals a sub 0 times 2 to the negative t over 5,700 years power. divide both sides by a sub 0. 0.6 equals 2 to the negative t over 5700 power. Change it into logarithmic form. Log base 2 of 0.6 equals negative 2 over 5700. We're trying to solve for t. So this is kind of like that first problem where I'm going to multiply both sides by negative 5700. The 5700s cross out and negative times negative is positive. So I get t equals negative 5700 log base 2 of 0.6. Using the change of base formula, I get negative 5700 log 0.6 over log of 2. And we're going to have parentheses there and there. And that goes into the calculator. Negative 5700 log of 0.6, close it up, divided by log of 2, close it up. And I get 4200.7. So they say about 4200 years. All righty. So for tonight, you've got a few problems using the change of base formula. And then you've got this new formula, the half-life formula. Tomorrow during the review, I should remember this, but if I don't, remind me to give you a list of formulas that you can have on a little card during the test, okay? And it's considered legit. You're allowed to have, I'll give you what those formulas are. The change of base, what's that?
Is that tomorrow when we go over the review?
Yes, yes.
Okay, I'll remember.
Okay, I'll bet you will. All right, so I'm gonna stop the recording.